Hello everyone, I'm Chen from Lanzhou University. Today we will present our work titled CrossMapping, Harmonizing Memory Consistency in Cross-ISA Binary Translation. As computer architecture develops rapidly, many processors with new ISA like ARM and RISC-V has emerged. Due to their cost-effectiveness, low power consumption, and stable licensing, many manufacturers are shifting from x86 to these new architectures. Since programs are intrinsically incompatible across different ISAs, dynamic binary translation is essential. DBT emulates guest program on the host by translating code at runtime. The typical workflow includes two steps. First, the guest motion code is translated into intermediate representation by the front end of the translator, and the IR code is optimized. Then, the IR is translated into host binary motion code by the back end of the translator. Basic blocks are usually cached to avoid redundant translation. The memory mode describes the behavior of concurrent primitive on shared memory. Due to different design choices, ISAs has different memory modes, resulting in variations in concurrent primitive and their behaviors. For example, for load and store instructions in x86, only load-store pair can be out of order, whereas in ARM, all four instruction pairs can be out of order. Due to the different memory modes across ISAs, harmonizing memory consistency from guest to host in DBT system presents significant challenges. As shown in the message passing test, X and Y are two registers, and A and B are two memory addresses. In x86, after execution, the result where A equals 1 and B equals 0 will not occur. However, if this test is native translated to ARM without inserting any barriers, the result where A equals 1 and B equals 0 may occur due to the out-of-order execution of load, and store instruction pairs. Therefore, it's necessary to insert barriers during the translation process to ensure correct execution on the host. Conversely, when translating from a weak memory mode to a strong memory mode, many barriers become redundant and need to be eliminated to avoid unnecessary performance loss. There have been some recent work propose methods to harmonizing memory consistency. QEMU adopt mapping schemes as shown in the table. During translation process from guest to TCJIR, a fence is inserted before each memory access to order any predecessors. In the translation process from TCJIR to host, TCJIR fence is translated into a sufficiently strong host fence to ensure both host and guest have same memory ordering. However, this scheme can lead to performance loss due to the insertion of overly strong barriers. For instance, the scheme inserts DMB4 before all store instructions. In practice, DMD load for load store pair and DMD store for store pair will be sufficient. Another issue arises with RMW instructions. QEMU translates RMW instructions with additional barriers by calling helper functions, which may result in incorrect results. For fetch and add, on x86, it is accomplished by a single automatic instruction, lock xadd, where on ARM it involves an acquire load exclusive and release store exclusive pair. However, acquire load exclusive on ARM may execute out of order with the preceding load instructions, potentially leading to incorrect results. Risotto and lasagna are two representative work on x86 to ARM mapping. They can handle RMW instruction correctly and more effective compared to QEMU scheme. However, they are designed specific for translating from x86 to ARM and are difficult to port to other ISAs. ARMOR is a framework designed for specifying and transforming memory modes. The framework leverages finite state machine to reduce redundant barriers in sessions, making it more effective, but it is not designed for cross-ISA DBT system. Motivated by these issues, we developed CrossMapping to provide quick and effective mapping scheme and support generic cross-ISA DBT system. The figure isolated an overview of CrossMapping, include offline and online stages. The mapping process occurred in two steps at the basic block level, guest to IR and IR to host. In the offline phase, CrossMapping simultaneously derives these two mapping schemes, named the FSM of mapping from guest to IR and the fence mapping from IR to host. In the online phase, conducting these two mapping within the DBT system can achieve the preservation of the guest memory orderings on the host during execution. Next, I will provide a detailed exploration of the derivation method for the mapping scheme. Firstly, we introduced a memory mode normalizer to describe memory modes using specification tables. Generally, the memory order of an ISA is described with one specification table, and the order enforced by each barrier is described with a separate specification table. As an example, the table shows the memory order specification tables for ARMv8 and its load fence, DMB load. The symbol checkmark denotes a pair of ordered memory access, and null denotes auto-ordered memory access. Each cell in the specification table specifies whether the memory access instruction of the type in the row header must be ordered with subsequent access of the type in the column header. The specification table for ARMv8 and DMB load have different rows and columns, which make direct comparison impossible. Same issue also arises in specification table of different memory modes. Therefore, it's necessary to refine the rows and columns of the specification table into matching partitions. The refinement is carried out in two steps. The first step is to found the set of memory accesses that serve as row and column headers, refining the specification table to have the same rows and columns. Partition refinement technique can be used to merge the rows and columns from different specification tables into a final grid partition. The second step is to fill in the cells of refined specification table. This can be inferred by the context of the original cells and the semantics of the refined set of memory access. After refinement, each specification table has the same rows and columns, enabling comparison and analysis of them. The comparison of a specification table is conducted by analyzing any pair of corresponding cells. If a table A can satisfy all memory orderings of another table B, then table A is considered to be greater than or equal to B. Union operation product a specification table that has a strings greater than or equal to each import table. Subtraction products a specification table that the ordering enforced by first table but not the second one. The FSM gets the mapping of the guest to IR, as shown in the figure. When DBT ends the beginning of a basic block, the FSM is initialized to the start state that the ordering are enforced in the guest but not in the host. Each state in the FSM represents the memory ordering described by a specification table, and the ordering should be enforced at a certain moment on the host. Each transition condition is a concurrent primitive. The FSM output funds that should be inserted according to create state when encountering concurrent primitives, and transition to new state after the concurrent primitive. We have designed an algorithm for generating FSMs, which handle 4 different cases. For fans, just map them directly to IR fans. For single instruction RMWs, which can act as 4 barriers, it's necessary to check if the host has a corresponding single instruction RMW. If the host has a corresponding instruction, then conduct the direct translation. If not, the RMW is decomposed into load and store accesses, and fans are inserted sequentially to emulate a full barrier. In case where the previous operation is a single instruction RMW and no other concurrent primitive are encountered at the end of the basic block, it's necessary to insert a barrier to ensure the RMW composed of load and store accesses can act as a full barrier. For other memory accesses, fences are inserted to comply with the required memory orderings. In the mapping process from IR to the host, direct mapping IR fence to corresponding host fence is sufficient. The IR to host fence mapping scheme can be generated by the fence comparator by analyzing the specification tables of both IR and host fences. For each IR fence, the comparator initiates the weakest host fence to satisfy all the enforced ordering of IR fence. As a case study, we have exported a mapping scheme from x86 to ARMv8 based on QEMU. The FSM have 5 states: start, after fence, after load, after store, and after RMW. When a concurrent primitive is encountered during the translation process, the FSM will output a sequence of IR instructions and transition to a new state. For example, in start state, encountering a load instruction would output load fence and the load instruction in IR and transition to the afterload state. To validate the basic function of CrossMapping and evaluate its translation performance, we implement 4 mapping schemes: x86 to ARMv8, x86 to RISC-V, ARMv8 to x86, and RISC-V to x86 based on QEMU, and conduct a performance evaluation using parsec benchmark. For strong on weak architecture emulation, additional fans should be inserted to enforce memory orderings on weak memory mode, which introduces extra overhead. We first assess the overhead caused by QEMU's fence insertions. Testing the performance without fences, we found that the additional fences occupied a significant portion of the execution time in benchmark. For x86 to ARMv8 translation, the extra fences accounted for up to 84%, averaging 52% of runtime. For x86 to RISC-V, they reach up to 81%, averaging 59%. These results indicate the necessity of reducing fence insertion while ensuring program correctness in strong on weak architecture emulation. Comparing our scheme with QEMU, For the x86 to MV8 translation, improvements reach up to 15.8%, with a geometric mean of 8.5%. For the x86 to RISC-V, improvements reach up to 12.7%, with a geometric mean of 7.3%. In the case of weak strong architecture emulation, only the redundant fences need to be removed. Comparing our scheme with QEMU, both schemes remove redundant fences. However, QEMU removes redundant fences in the TCG-IR to x86 mapping stage, while CrossMapping removes them in the MV8 to TCG-IR and the RISC-V to TCG-IR mapping stage. Removing fences earlier reduces the overhead during translation, thus improving the geometric mean of the MV8 to x86 translation by 1.9%, and the RISC-V to x86 translation by 2.8%. Thanks for your attention.